In today's note, we're going to look at restrictions and function notation. So the first thing is restrictions. And what are restrictions? Well, restrictions are limits that we put on equations. Basically what they do is they restrict what values of x for the equation works for. In other words, we can call it the domain, which we'll look at in a later note. So if we have an equation y equals 4x plus 2, and we have some notation here, which is saying that x is greater than 4, this little part over here, the x is greater than 4, that's our restriction. And the meaning of this is that the equation y equals 4x plus 2 only exists at x values greater than 4. So if I look at x values less than 4, I should not see this equation, or I should not see a line or anything on the graph. Other notation that we could use, right? So if we're using this symbol as the symbol up here as the greater than, we also have less than. We then have also the greater than with a line under it, or equal to. So greater than or equal to. We have less than or equal to. We have equal to as well. Now again, yes, we're using these symbols with these definitions, but keep in mind the symbol. So if I look like that, remember the symbol, it always opens up to the larger one, or if you want to think of elementary school as an alligator mouth, it eats the larger one, or the larger number. So if this symbol opens up to a number, that means that number that it's trying to eat or opens up to is the larger number, or it's greater than that. So, for example, if we want to look at the following graphs, we see a bunch of different functions, and we want to write the limits for each function. So, for example, if I look at the y equation in the red, right here, just tracing over it so we can see it a little bit better. So this line right here is our our one function in red, and we want to add the restrictions, because normally this function would keep on going up like this. However, it seems to be stopped right at this point, so it's restricted, but we can see that it continues on backwards forever. So how we would write this is we use a squiggly line. This value is that for when x is less than or equal to 3. That's when this function works. When x is less than or equal to 3. So again, and the mouth opens up to eat the 3 because the 3 is the larger number. For this section here, this green section, the next one, we can say that the restrictions are for when x is greater than or equal to 3. So we're going to put 3 here, x is greater than or equal to, but x is also less than or equal to 5. Because this green function does not go any further from 3 to 5. So it exists everywhere in between. For our purple function over here, we can see that this function exists from 5. So 5 is our lowest number, so x is going to be greater than or equal to 5, but less than or equal to the endpoint, which in this case is 8. For our orange function here, again, we're looking at the start and the end point of the function, so it starts at 8, so that means that this function is greater, the x values are greater than or equal to 8, but less than or equal to where it ends, which in this case is 11. And then finally, this blue function here, the x values that it's restricted to are 11. So we can say that x is greater than or equal to 11, but less than or equal to 18. And those would be our restrictions. The other thing that we're looking at in this note is our function notation. And what the function notation is, it's basically any relation that is a function can be expressed using it. It's just a different way of writing it. And the key thing is we use f at x, or f bracket x bracket, in place of y. So instead of writing something, say for example, y equals x squared, we can be writing it as f at x, or f with a bracket x, equals x squared. And the way you pronounce it is you either say f at x or f of x. Basically what this means is that x squared is a function that uses the variable x. We often can sometimes see f at x or g of x, but it can be specific to the variables of the function. This is just basically saying two different functions. So one function is f at x, another function would be g at x. Again, we can also replace the x with whatever variable we're using. An example would be in a height and time function, like setting a rocket off and measuring its height over time, we might use a formula, say h at t, or the value of h, or a function of height, using the variable t for time, is equal to negative t squared, 5t squared plus 15t. And this is basically then a function that uses the variable t. The reason we use function notation is just an easier way to write, because we can use function notation to generate points on a graph or solve for an unknown. So if I take that same equation above, h at t equals negative 5t squared plus 15t, I can change that to say h at 0. And what h at 0 is, it's basically saying the function of height when time is equal to 0. So in our equation, we can now see that because that t is changed to 0, the t's in our function has also changed to 0. So what that means is that when time is equal to 0, our height is equal to 0 meters. Or at 0 seconds, the height is 0 meters, basically, or also as a graph or a point, the point is 0, 0 on a graph. So basically this is just an easier way of saying, instead of saying solve the equation y or h equals negative 5t squared plus 15t, we can just, or when t equals 0, we can just say h at 0, and then we should know that we have to solve when t is 0. So another example, just taking that same idea, if we have h at 0.5, that means I have to take my original function, h at t equals negative 5t squared plus 15t, and h at 0.5 means that everywhere I see a t, I have to replace it with 0.5. And now once that is done, now I'm just going to go through and solve. So if I have 0.5 squared, I have negative 5 times 0.25 plus 7.5. So I get 1.25 plus 7.5, I get 8.75 as my final answer. Now, you may feel compelled to solve for h and thinking that h bracket 0.5 is actually h times 0.5, but that's not the case. We don't need to do anything else because, again, we have to recognize that this first part here is just basically saying I have to solve for the function h when t equals 0.5. So this is the final step, we'll say. And we'll put in brackets do not need to solve for h, because we've already figured out that the function h when t equals 0.5 is our answer here. Right, so when h at 1 is the same idea, I'm taking that original function, and everywhere I see a t, I'm just replacing it with 1, because this is saying the function h when my variable is 1, and my variable in this case was t. So negative 5 times 1 squared is negative 5 plus 15 equals 10. So that means when h is, or when t is 1, the h, or my height, is 10. H at 1.5, again, same idea. It's everywhere the t was, I'm going to replace it with 1.5. And I'm going to go through and solve. So 1.5 squared, we have negative 5 times 2.25 plus 15 times 1.5, 22.5. We have negative 11.25. So in the end we get 11.25. So h at 1.5 is equal to 11.25, or the height at 1. Based on the scenario that we are looking at. And in the end, finally, h at 2, same idea. Everywhere I see a t, I'm replacing it with 2. So it becomes negative 5 times 2 squared plus 15 times 2. So we have negative 5 times 4 plus 30. Negative 20 plus 30 is 10. So that means h, or the height at 2 seconds, is 10 meters. So if we had to use the function notation but with a graph, it's a little bit different, but it's still the same idea. So on my graph here, I can see that I have the function, and we're calling it g of x. So g of x, or instead of y, just saying g of x. And in our first step, we want to figure out when g, or g at 3. So what that's saying is we need to figure out what is the value of the function when x equals 3. So if that's the case, we have to go over on our graph until we hit 3, and then we follow that up until we hit a point on our graph, or on our function, and that value there is g at 3. And if we look, we can see that it lines up at 2. So that means that g at 3 equals 2. If I want to do the same thing, g at negative 1, it's the same idea. I'm going to go over to where x is negative 1, and I'm going to follow it up till I hit my function, but luckily I don't have to go up very far because my function is right at that value. So that's g at negative 1, and if I look at the value of that, g at negative 1 is equal to 0, because it's right on the x-axis. Another way I might look at it is I'm looking for x if I know that my function is equal to 1. So in this case, I know that my function equals 1, so I have to go to the y value of 1, which is right here, and I need to figure out what x value gives me that function value. And if I look at when g equals 1 and go down to the x-axis, it's right at 0. So that means g at 0 equals 1, or x equals 0. So when you're using a graph with function notation, you're just basically finding the y value for a given x value. So in our last example, we're just basically using this in a certain notation or just different context or specific scenario. So the relationship between the selling price of sunglasses and revenue is represented by the function R at S is equal to negative 10S squared plus 800S plus 120. So the graph of the function is shown to the right here. We want to determine the revenue when the selling price is $10. So if I'm using my graph, I go over to where, or basically what this is saying is I want to figure out R at 10. So if I go over to my graph, I find where 10 is and I go up until I hit my function, and I go over to my y-axis and I see where it hits. And in this case, it looks like it hits at 7,000. So a value of 7,000. So that means that the revenue, when the selling price is $10, the revenue should be 7,000. If I'm using the function, I'm doing the same idea, R at 10, except instead of using the graph, I'm going to use the actual function to solve for it. So instead of S, I'm going to have 10. So everywhere I see the S, I replace it with 10, and then I just go through and solve. So we have negative 10 times 100, negative 1,000 plus, negative 1,000 plus 8,000 plus 120. We should get 7,120. So we're slightly off, but again, because we're using the graph, we're trying to see as close as where it touches. So because the scale is quite big on the y-axis, we're going up by 1,000. It may be that we just can't accurately see exactly where it touches based on the scale of the graph. If we were to zoom in on the graph, right, if we were to zoom in, or if we were to actually zoom in the actual graph, we might be able to see a more precise value of where it actually meets. But we can see that we're still fairly close, whether we're using the graph or the function. So the other value, or the other part, B, what does R at 20 equals 12,120 mean? So basically what this is saying, this, remember, is the S based on our function. So basically this means when the selling price is $20, the revenue is $12,120. So when our selling price of sunglasses is $20, the revenue is $12,120. And basically for their C, if R at S equals 16,120, determine the selling price. So this is our revenue. So we want to figure out, okay, if I have a revenue of $16,100 or $16,120, what is my selling price? Or in other words, when Y equals 16,120, what does X equal? So I'm going to go to my graph. I'm going to find 16,120. I can see that it's roughly right here on my graph, right at the very top. Follow it over. And now I just need to basically draw a line all the way straight down to my x-axis to figure out what that value is. And we can say that it's roughly $40. So the selling price is $40. So again, the key thing from this note is just understanding what restrictions are and just understanding function notation.